Hello everyone, welcome back to the UCrew video lecture series. Today we're just going to go over some general assessment principles and some things you should know going into your first assessment. Just a quick overview of what's ahead. We're going to start with a brief introduction into energy and power, units we use here as well as in the energy industry as a whole, how to read utility bills, we're going to learn about nameplates on machinery, and we'll end with some typical assessment findings that hopefully you guys will find kind of interesting. First up, energy and power. Hopefully most of this will be a review from physics, but just in case it's not. Power is the rate at which electrical energy is transferred by a circuit. Voltage is the electrical potential difference between 2 points, and current is the flow rate of charge past a particular point. Or in other words, is the amount of electrons carried through a wire. If you're ever wondering how to go between these, there's a nice little pie chart you can reference down here. Let's say you know the current and voltage and want to know the power. From this pie chart, you can see that power is equal to voltage times current. Talking more about energy and power, we see a couple different types of electricity here, although typically you don't have to worry about this too much, just something we want you to know about. There's DC or direct current, which is the red flat line you see on that chart, and this comes primarily from solar panels or batteries. Then there's alternating current, and this is exactly what it sounds like. It's more of a push and pull rather than the stagnant direct push from DC current. And this is the most common type of power coming from the grid. This is the type of current you get plugging something into an outlet. Additionally, we see single-phase power and three-phase power. If you want to learn more about this, there's a bunch of super great YouTube videos, like the one here from the Engineering Mindset, that can explain these differences a lot better than I would be able to. The basic takeaway is that three-phase power can deliver a higher amperage, voltage, and therefore power to large energy users. It is the most common power in an industrial plant. In your home, this might be your dryer or oven. This power comes from three phases or legs, which are three separate lines that go into the machine. Getting even more into the weeds now, how do we quantify the energy use of a building? How do we know if they're doing it efficiently? Well, one of the things we look at is power factor, and this is the ratio of real power to the apparent power. So what does that mean? Well, there's a nice little graphic down here that kind of explains it. Real power is the actual amount of energy that an equipment's consuming. This is the liquid part of the drink. Whereas the total power is the amount of energy going into the equipment, the total amount of electricity that you're paying for, even if you're not making good use of all of it. This is everything that's in the glass, including the liquid and the foam. Always, 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 you want to see a high power factor, meaning you're effectively using all of the electricity you're paying for. You don't want to be paying for a glass of this refreshing beverage down here and half of its foam. If you don't have a high power factor, that's okay. Lucky for us, there's some ways that you can adjust your operations and increase it. Next, we have peak demand and load factor, and these two happen to go hand in hand. Peak demand is the highest electrical demand from a facility. And again, this is talking about power. The high point on this chart down here is the peak demand, and facilities are charged on their monthly electricity bill for the highest volume of demand used over a 15-minute period. It doesn't matter if for the entire rest of the month you only used a little bit of electricity, you'll still get charged for whatever the peak is, no matter the amount of time that it lasts. That brings us to the second item on this slide, which is the load factor, and that describes how equivalently you're using power throughout the day. Similarly to power factor, ideally you'd want to have a high load factor, and you'd want to have a low power demand. This facility could decrease their bills by using less power during that peak and using a little bit more at other times of the day. This might be a little confusing now, but don't worry. This is something you'll get super comfortable with as you move forward in your work here. Now, something that's super easy to confuse when you're just getting started is the distinction between power and energy. As a reminder, power is the rate at which electrical energy is transferred by a circuit. This is the red line down there, which represents the power draw over time from a facility measured in kilowatts. Energy, on the other hand, is the total capacity to do work, or in other words, the total amount of electricity used. A basic analogy to help you understand this is that power is like your velocity and energy is like your distance. When you integrate velocity with respect to time, you get the total distance traveled, which is the area under the curve. Similarly, when you integrate power with respect to time, you get the total energy used. This is measured in kilowatt hours, which is the equivalent of if you used 1 kilowatt of power for a 1 hour time period. Another analogy would be if power was the flow rate of water moving through a pipe, energy would be the total amount of water that went through the pipe. Just to help you along with some of the things we've covered, here's a few helpful equations. The efficiency of a piece of equipment is equal to the mechanical power output divided by the electrical power input. This basically measures how effectively that machinery uses the electricity supplied to it. Now that you know about three-phase electricity and power factor, we can make a slight correction to our power equation from earlier. The power draw for a piece of equipment using three-phase electricity is the square root of 3 times the voltage times the current times the power factor. You've already seen these now, but it's worth reiterating that the power factor is the true power divided by the apparent power, or otherwise the amount of power that you're actually paying for. And the load factor is the average load divided by the maximum load. Now that we've gone over some of the key concepts, we can go over the units we use to describe those concepts. First, we're going to get into the units that you should always use when talking to facility staff. Voltage, as you can probably guess, is measured in volts. Current is measured in amps. Electrical power is measured in watts, but we typically talk about kilowatts. Facility staff usually have a much better understanding of that since that's how power bills are structured. Anytime you're talking about motor power or air compressors, those will be in horsepower, like a car engine. And electrical energy is measured in kilowatt hours, which is equivalent to if you're using 1 kilowatt of power for a 1 hour time period. Some other units we use, as well as in the energy industry as a whole. First, we have thermal energy, which is measured in British thermal units, or BTUs. But like how we use kilowatts instead of watts, we use megabtus, or MMBTUs, equivalent to 1 million BTUs. Anytime we're talking about cooling power, like for a chiller or refrigerator, we'll be talking in tons, or tons of refrigeration. Volume is always in gallons, temperature is always in Fahrenheit. Brightness is measured in lumens, which is a little hard to explain, but you'll come to understand this one through your work too. Volumetric flow is measured in standard cubic feet per minute, or SCFM, and you'll very often see this for compressed air systems and HVAC. And lastly, anytime we're talking about pressure, it will always be in pounds force per square inch, or PSI. A couple useful conversion factors I want to throw at you, but I'm not going to get into them too much. One that I do want to point out is the decatherm, or DTH, which is equivalent to 1 MMBTU. This is important because when you're looking at natural gas bills, they'll be billed by the decatherm. We then do our calculations and report them back to the DOE database in MMBTUs, which I know makes a ton of sense. Let's keep it moving. Now that we know the units we'll use, what are some you shouldn't use? Well, pretty much anything that's metric. I know these are units you're used to seeing in class and they have easier conversions, but they largely aren't used in industry in the United States. Don't talk about joules or joules per second, especially this one, just say watts. Don't say meters, Celsius, talk about calories, cubic meters, liters, or pascals. Again, all our assessments are in the United States, and using any of these is going to catch you some funny looks from facility staff. Using these can make them feel like you think you're smarter than them, which for one is just never a good assumption to make. Just because you're going to college and getting your fancy engineering degree does not make you more uniquely intelligent or qualified than the operators and facility staff you're talking to. And two, we're trying to sell them on our ideas. The facility staff liking us and feeling like they can talk to us on even ground goes a really long way on that front. One other thing worth mentioning is outlet standards. In your house and residential areas, you'll be using 120 or 240 volt single phase electricity. And industrial areas, you'll use that same 120 or 240 in office spaces. But in manufacturing areas and for process equipment, these have a much greater electrical demand and will thus be using either 230 volt or 480 volt three-phase electricity. And for those of you that are curious, in the US, these will always be at 60 hertz for alternating current. Now we're going to talk you through how to read utility bills, specifically electrical bills, natural gas bills, and water bills. We're going to start with electrical bills and go the most in-depth here since they're the most complicated. On an electrical bill, you will find facilities charges, demand charges, usage charge, power factor charge or power factor adjustment, interest charge, sales tax, and then additional fees and fixed charges. As you might be able to tell, you're now looking at an electrical bill. The top might look a little bit confusing, but you can see that this is just for 1 meter. The first thing I want to highlight is the power factor. This facility has a power factor of 0.89, and if you remember, 1 is ideal, but this is pretty good. In fact, for power factors above 0.9, they don't even include it on the bill and don't penalize you for it. So this facility is almost where they should be. The way the power factor charge works is an adjustment for the demand. Since their power factor is below that minimum threshold of 0.9, they're now going to be paying for 1 extra kilowatt for both the demand charge and facilities charge. Next, I want to highlight the demand and facilities charges. These are both charged on the basis of the peak demand in kilowatts after the power factor adjustment. Here you can see the facility's peak demand for this month was 92 kilowatts. Again, this doesn't mean they're using 92 kilowatts all of the time, just that their highest power draw at any point in the month was 92 kilowatts. Right below that, you can see that they use 18,800 kilowatt hours of electricity during this month. If you think about one of those power draw versus time plots we looked at earlier, the kilowatt hours are the area under the curve, or the total amount of energy used during that time. Usually in Utah, we see about 3.5 cents per kilowatt hour, so this is a pretty typical rate. Below that, and up top with the basic charge, you can see some of the miscellaneous charges and fees that show up on the bills. There isn't anything we can do with this, it's just nice for you to know what you're looking at, and if the facility staff ask what exactly they're paying for. Some of these are paid at a flat rate, and others fluctuate with the total bill. These mostly go towards funding state programs, like providing energy to low-income Utah residents. Below all those are taxes. The municipal energy sales/use tax is paid to the local area the facility is in, such as Salt Lake City, while the Utah sales tax non-residential is tax paid to the state of Utah. That second part is interesting here, since manufacturing facilities are typically exempt from paying state sales tax on energy purchases. Again, that's just for state taxes, not municipal. So it'd be worth mentioning to your team lead that this facility is paying those state taxes and see if there's a recommendation to make there. Then lastly, at the bottom is the total new charges, which is the sum of everything on the bill. One other thing that can be helpful to get an idea about how the facility is using their energy at a glance is this nice little graph on the right. This just shows their average daily electricity usage for the 12 months leading up to this bill. These are the kind of graphs that you'll be making anyway with the bills you're analyzing, but it is nice to get a quick reference for what their electricity consumption looks like, and if it's changed since the previous year. Here's another electrical bill with a couple key differences. First, I want to again point out the power factor, which in this case is 0.7963. This is a decent bit lower than the last bill we looked at, so as you can see, they're getting penalized heavier than the previous one. The real important distinction between this bill and the last is that they're only paying the facilities charge and not the demand charge, and they're paying different amounts for electricity used during on-peak hours and off-peak hours. So what does this mean, and why is it different from the last one? Well, on-peak refers to the time when most manufacturers will be working and people will be using a lot of electricity. This is 7 a.m. to 11 p.m. during the weekdays. All other times, like nighttime, the weekend, and holidays, are considered off-peak. Utility companies want to encourage people and businesses to use more of their electricity during off-peak hours, since it lessens the strain on the power grid and makes it easier for the utility to keep up. One way they incentivize this is by offering different rate schedules, which decides the way you get charged for your utilities. The last bill we looked at was on a schedule where you paid for peak demand and their electricity cost the same at all times of day. This bill is on a schedule where they pay less for that peak, pay for really expensive electricity during the peak hours, and really cheap electricity during the off-peak hours. This is usually good for facilities that operate 24/7. The last short note for this bill is that you can see they're paying municipal sales tax, but not state sales tax. Okay, so now we're looking at a gas bill. What you'll immediately notice is that these are much simpler than electricity bills, and there's a lot less pieces of information you need to pull from it. So what do we need to know? Down here are the number of days over which this bill was charged and the amount of decatherms used. Remember, a decatherm is equal to an MMBTU. Up here is the total charge for that natural gas at an average rate of 550 per decatherm. You'll notice they're not paying any state sales tax, only municipal, and down here is the total bill charge. Remember how we talked a little bit about rate schedules for electricity? Well, they're a thing for gas too. You can see these guys are on the GS rate schedule, which means general service. You'll also see a similar graph as on the electricity bills, only this is showing the total gas usage in those months. From this graph here, you could deduce that this facility probably only uses natural gas for heating, since they use a lot in the winter and then nothing or close to nothing in the summer. Okay, lastly, we're going to briefly touch on water bills. A lot of facilities won't even have you look at water bills, depending on their production and how their building is operated. But there can be some solid savings with water when it comes to things like irrigation. Like natural gas bills, there's not a whole lot to look at here, so we don't need to spend too much time. Up here's the water usage and related usage charge. This is charged per unit, which in this case, as you can see at the bottom, is 1,000 gallons. Here's the fees that you don't need to worry about, some of which are actually calculated as a function of the square footage of the property instead of the water usage. Little fun fact for you. Down here's the total for the bill, and over here is the previous month's usage. Now, water is almost always a local utility, like through the city the facility is in, rather than the large corporations like Rocky Mountain Power or Enbridge that supply electricity and natural gas in Utah. So water bills can vary a lot in how they look, but this should give you a solid foundation at least of what you can be looking out for. That was a lot of talking about utilities and bills. Now we're going to pivot a little and talk about nameplates and machinery. So almost every piece of equipment you'll see in the industrial setting will have a nameplate, and the nameplate gives you invaluable information on how the machinery operates, and most importantly, what machinery you're actually looking at. The three main pieces of info you need to figure out are the manufacturer, the model number, and the serial number. Now, every nameplate's different. There's not a cut and dry template that everyone uses. Just make sure you take pictures of any equipment nameplates you come across so we can all reference them later. Also, take a picture of the machine itself and record the location of the machinery just in case you want to go back and verify anything. Okay, so here's an example of a nameplate. So what can we learn from this? Well, we can see the manufacturer. This is the Kaiser compressor. Over here's the part number or model number. Those are the same thing, and the serial number. You can also usually find some other useful information on these. For example, right below the serial number, you can see that this compressor is rated to a maximum pressure of 125 psi and a maximum airflow rate of 71 cubic feet per minute. Okay, that's cool and all, but why do we need this information again? So we can get a data sheet, of course. Again, we're trying to identify what piece of equipment we're looking at so we can get this information. Data sheets are incredibly valuable as they tell you about the standard operating procedures of the machinery, how it's meant to perform, and under what conditions. Additionally, we're able to find the efficiency on most pieces of equipment. Okay, lastly, we're going to cover some of the typical findings for our energy assessments. So what kind of equipment do we usually look at? Well, we almost always see compressors and HVAC units. And for those of you that don't know, HVAC stands for heating, ventilation, and air conditioning. So anything that's related to AC or heating. Also, quite commonly, we'll see boilers, motors, pumps, and cooling systems. Now, these are just some of the common ones. Every assessment is a little bit different, and these aren't the only kinds of systems that we work on. One of the things I really enjoy about working here is the variety in the different types of facilities you get to go to, the different types of recommendations you get to work on, and all the different systems that you'll see. This last slide is just a nice little pie chart that kind of outlines how a typical industrial facility uses their electricity, which I find kind of interesting. This kind of shows where we should generally spend our time. If the only thing we ever focused on was HVAC, we wouldn't make too big of an impact. That's not to say that it isn't valuable to look at HVAC, it totally is. Any little bit helps. But our main goal is to make a big impact on their big energy users, like pumps, motors, and compressors. All right, folks, that's about all I have for you in this one. I hope you found this informative and hopefully at least a little bit interesting. Thank you.